The first problem that we are going to look at is basically the sorting problem. Problem statement basically is that, look, given a list of numbers, we want to sort it, for example, in an ascending order. We have spoken about this before. Previously, we learned three algorithms for this purpose: selection sort, insertion sort, and bubble sort. We will now see another algorithm based on heaps, which is called heap sort. Now, when we spoke about selection sort, insertion sort, bubble sort, we also saw that they are basically complexity of, let's say, order of n square. It turns out heap sort is going to do it much, much, much faster in an order of n times log n. And in fact, that is a significant improvement compared to the algorithms that we have seen before. In fact, heap sort can be seen as a better version of selection sort. Remember, the idea in selection sort was always to pick or select the minimum item and put it in the beginning. Now we can clearly sniff a heap over here. Heaps basically, remember, by structuring data in a certain way, bring out the smallest item to the root, and they have this magical ability to restore the heap structure once again, even after the root has been extracted. So that's the basic idea of heap sort, and clearly we can see that heaps are going to give us a lot of improvement in efficiency. So the algorithm basically broadly is in two steps. First step, done one time, we heapify the entire list to get a min heap. We'll see an example of this later. And thereafter, we keep on extracting the root item. Remember, root item is the smallest item, and we keep putting it in another list. So once we extract the root item, we need to restore the heap structure back. We again saw this in the last lesson. The way we are going to do it is that we are going to bring the last item to the top, and then through a percolate down mechanism, find the right place for the last item so that the heap structure is restored again. And once again, the smallest item comes to the root. So we keep on doing this for every item. And as you can imagine, the entire list will get sorted. Now, in Python, using heapq.heappop, in fact, we can do 2, 3, and 4 like in one command. So it becomes very easy to write the code. We'll see this later. But let's try to understand this with an example. Let's say we have this list to sort. So 9, 19, 16. This is clearly not a heap, but we do a one-time effort to heapify this. You notice I convert this to a min heap. One has come to the top, the root, because one is the smallest. Thereafter, the value of the parent is less than the value of the children. So that's basically a min heap. This is done once. We go and extract the zeroth item, the smallest item, to another list. So that is my smallest item. Now, once I do this, remember, I've got to restore back the heap structure. So to do so, I'm going to put this 14 on top. So one has been extracted, remember, so list has become smaller, but I bring 14 to the top. And now 14 being on top, my min heap property is violated. However, in just two comparisons, I realize that 14 should move here, and then in fact 14 should move here. So we again restore the heap in just two comparisons. Notice this part is completely unchanged, and that's because the sift down operation or the percolate down operation only goes on a particular branch which is impacted. And we have seen this before. Now we see that 3 has become the root. We extract 3 into a new list. Again, I'm going to move 9 to the beginning. So list becomes shorter. I bring 9 to the beginning. Now clearly this is not a min heap. But again, with percolate down, just one swap, just one comparison, a swap, and we again have a heap structure. Once again, the root item is the smallest item. I extract it to a new list. So you notice the new list is starting to form, and I bring 16 to the top. So I do that. Once again, min heap structure is violated. I do a percolate down to get my 16 to, let's say, this position. 8 comes on top. 8 being the smallest is the root now. I extract it. I keep doing this. So 19 on top. I restore it back. 9 comes on top. 9 is a new root. I extract 9 on there. Then 14 becomes a new root once again after percolate down. Then 16 and then 19, and the entire list is sorted. So you notice it's basically like selection sort because we are always selecting the minimum, but it's more efficient because this percolate down action that we saw, including let's say from here, all of these slides, happens in log of n time, and that is actually significant compared to the selection sort where it was basically a linear operation which resulted in the overall complexity being n square. We'll see this in more detail later on. Now, before wrapping this up, I just want to make one point which is kind of interesting here. Remember when we looked at selection sort, insertion sort, or let's say the bubble sort, we did those algorithms in place, which means that the list items were kind of swapped with each other based on some rules. We spoke about them, but there was no need to create any extra space whatsoever. So it all happened within the same list. Once created, it just swaps items to create us, let's say, the sorted list. But clearly, in our development of heap sort, we spoke about another list that's holding the sorted values. So this is not in place. In fact, this requires some extra space to be created. The reason we are doing this is because we are using Python's heap module, and it's just much more conducive to do it this way. And since our focus is on understanding, let's say, the philosophy behind this, it's perfectly fine. However, if you want, you can also do an in-place version of Heapsort. But then for that purpose, we have to write our own heapify function. I'm obviously encourage you to try this, and that will be rewarding. One very interesting point is that when we want to sort a list in an ascending order, in fact, we create a max heap and bring the max item to the top. And the reason for that becomes clear as we start looking at the heap structure more closely. Happy to discuss, but for now, this is just fine. In the next video, we'll write the code to the heap sort, and then we'll move on to evaluating its complexity and, let's say, runtime with respect to selection sort. I hope you found this interesting. Do look at our website www.ybyte.in and forever enjoy coding. Take care. Thank you so much. Bye bye.